that's the student paper. So. All right. So I'm here to talk about classification and about multilabel classification in particular. And then we introduce how to, say, combine this instant-based learning and logistic regression together to solve the multilabel learning problem. And for the people who doesn't know who's who, this is me. And I can say that. So basically, we are typical PhD student and professor. Right. Okay, so multilabel classification is everybody goes to Flickr, and then you know this tagging system like Flickr. So basically, you saw the picture and you give different labels to the picture. So for one single picture, it can at the same time have different labels. Like for example, this picture it can at the same time belongs to sky, house, the grass, and so on. And in social bookmaking, like for example, delicious, and for one particular website, like for example Twitter, at the same time it can belong to Web 2.0, social, community, blog, and so on. And actually, I think Robert just talked about this assembly website, which is also kind of a tagging system. It's also a multilabel system. And another example is, for example, Google Mail. And everybody using Google Mail here. And in the Google Mail, we also have this multilabel system, which from a finite set of labels, then you assign one single particular emails a different type of labels at the same time. So formally that, I mean, compared with this conventional classification is, in multilabel classification, instead of assigning an instance one single label, we, in the same time, we assign a set of labels to one instance. So this is the basic difference between the multilabel system and the conventional label classification problem. And you may already feel that this kind of multilabel learning problem is really an important and popular problem, both in practice and also in theoretical aspect. So there are already a lot of, say, quite a number of work on this multilabel learning problem, and most of them are model-based approach. So the idea is that I give you a training data, then you train a global model, and in the test time, you just apply this model, they give you the outcome, right? And, but on the other hand, if you think about it, this instant-based approach is so far not, say, intensively addressed. This is somehow strange because we know that in this conventional classification, in binary classification, this nearest neighbor instant-based approach is very strong, right? But in multilabel case, it's not yet, say, fully addressed. So one exception is maybe this MLK-NN approach. MLK-NN is an instant-based approach for multilabel classification, which is first proposed by Zhang and Zhou in 2007 at the recommendation. And this approach, instant-based approach, has shown very, very strong performance. Compared with a state-of-art model-based approach like Regression and adapters, is auto-performance in a lot of data sets. Okay, so there's two things here. First, it shows the potential of instant-based approach for multilabel classification. And the second is, even though that MLK-NN shows very good performance, but we still believe that the potential of instant-based approach is not fully exploited yet. And one major reason is it doesn't consider the correlation of labels, right? And actually, we believe that in multilabel setting, the correlation of labels run very important. For example, one paper which is belongs to computer science is more likely also, have the label mathematic rather than law. But this kind of label correlation is crucial for multilabel classification, which, by the way, is ignored by this MLK-NN approach. So in this work, we made the following contributions. We propose a new multilabel learning approach. And this approach combines nearest neighbor principle, combines instance learning, and logistic regression together. So in a sense, we've learned the distinction between the model-based and instant-based approach. And we take the correlation between labels into consideration. Right? So let's talk about the approach. The key idea is we consider the labels of labels as the extra features of an instance. For example, you get a data set here, and here, for example, this is the test instance, and these three are the nearest neighbors of this test instance. And now the question is, does this guy, this test instance, like basketball? To answer this question, we consider the label information in the neighborhood as an extra feature. For example, we have one artificial column here. Like here, for example, means that among the labels, the three labels, two of them like basketball. All right? This is our extra feature. So this is the key ID. And now let's work on this mathematics stuff. So let's consider a test instance, say x0, and let's define a distance between different instances. So this xi is one example from the training data, which we know the label, right? And then the posterior probability that this test instance has a positive label is given by this, right? Giving the label information of the training data and what is the probability that this label is positive. Let's, for now, let's just consider binary case, okay? Before we jump into which label case, we just first consider binary case. So we have these two things, and then just by apply, we look at this ratio, we just apply the base inputs. We immediately end up with this formula, right? So here the first part is the likelihood ratio, right? And the second part is just plot. Base inference. Directly we just come up with this. And just for the sake of simplicity, we denote this likelihood ratio with rho. All right? Okay, so then I take logarithm on both sides, then we just immediately come up to this. So this is the likelihood ratio, then plus some prior term here. Again, for simplicity, I denote this prior term using omega zero. Okay? So, so here's the idea. As I said, we want to use instant-based approach. So basically, we want to apply this nearest neighbor principle. If you want to apply this principle, which means that this likelihood ratio rho should be a function of this distance delta I. And the idea is, if there's a guy which is very close to me, has a positive label, and make me more likely to be also positive. This is the reasoning behind this. And there are different ways you can model this rho. And in particular, we define this in this way. You can define another way, but this is one particular way to do it. So here, so alpha is just a parameter. You can consider now it's a constant. So let's see how this rho behavior. We have different situations. One is delta is go to infinity. Let's say if there's a guy which is very far away from me, so no matter it is positive or negative instance, it should not have any influence on me because it's very far away from me. And if this instance is very close to me, then when it is a positive example, the rho goes up, which means make the positive instance for me more likely. Otherwise, rho goes down, which means that it makes me less likely to be a positive instance. Okay, so this is the dynamic of this function. And then what we have to do is we just consider the whole neighborhood of the test instance. Okay, we just sum up all the evidence from the neighborhood because we consider the IID sample, so you can have this big sum here, sum up the whole every instance in the neighborhood. And then, as you can see here, we denote this second part with omega plus. So basically, this omega plus is just evidence for positive class, within the neighborhood. And this omega zero is a biased term, or you can also consider it as a prior probability in a sense. Okay? So, we can look at it. Statistically, you look at it, you find out that this formula is nothing else than conventional logistic regression equation, right? And the idea is, if you take nearest label principle and you apply base inference, then you come down to realizing this nearest label with logistic regression. All right? Okay. So let's just copy this formula in the second slide. So it's the same thing. Let's say watch this problem from different angle. So far we talked about distance, but actually you can also consider this from a different angle in terms of similarity. The distance, similarity, conformity. So actually you can consider this part. Instead of distance, you can define a similarity function between distance. So in this sense that you can apply any similarity function you want. You can apply kernel if you want. Okay? In fact, by doing this, we can include the standard, say, KNN approach as a special case. What we have to do is we just set omega 0 to be 0, and we define a special kernel in this formula, which is if the instance in our neighborhood is 1, otherwise the similarity is there. If we define it this way, we can include the KNN as a special case. Right? So this is so much for the single level case. And then let's consider multi-level case. Actually, the idea is the same. We consider the neighborhood labels as extra feature. So when someone asks, does he like basketball? We consider the information for all the labels in the neighborhood. So basically, we got an extended representation in the following way. So similarly, this means that 1 among 3 neighbors like table tennis in this instance. Okay, this is extra features. So now, what you have to do is, you only have to solve one logistic regression for each single label. Okay, for example, if you ask, does this guy like basketball? Football. Does this guy like football? Then you just look at this equation. Okay, and you just solve this equation using logistic regression. The nice thing is, this alpha parameter which you got from logistic regression can tell you the appearance of this basketball. How does this appearance of basketball influence on this one's hobby on football? Right? It's very easy to interpret. Okay? And this omega plus is just evidence which you got from the neighborhood. All right? This is very nice because you can interpret the whole model very easily. Just for the sake of completeness, I wrote down this decision rule for you then. For multi-level prediction rule, you just consider the sign of this ratio. And if you want to output a ranking, you, instead of considering the sign, you consider the score of this function. Okay? So this is the decision rule. Now I start to talk about some parameters results. And all these data sets are multi-level data sets. So we really try hard to find this many multi-level data sets because it's not so easy to find multi-level data sets. And it's come from different domains, from music, computer version, biology, and so on. And we have tested on the following different approaches. Of course, we compare with MLKNN, because it's also an instant-based approach. And we also take another approach as a baseline, like the Banner relevance with logistic regression, simplifying KNN is base layer. And label power side is another baseline in terms of labeling. And of course, we also test on our approach, IBRR in there. And I want to say this is that for the sake of fairness, we set all the parameter settings the same as MLKNN. So actually, it's only one parameter, it's the number of k for the nearest label. We set the same as MLKNN, which is, by the way, 10. The 10 is the value which is suggested by this MLKNN in this paper, because the 10 leads to best result of MLKNN. So for the sake of fairness, we set the same as MLKNN. And we test on different, say, loss function or say different evaluation metrics for this multi-label learning. And I just wrote this definition here for sake of completeness. And actually, I just want to say the reason we take all these metrics is because it was also used by this American paper. So again, for the sake of fairness, we're using the same evaluation metric. And we have done a two-step statistic test. In the very first test, we applied a Friedman test, which to reject the null hypothesis that all the classified perform equally. Okay, this is the first test. We want to find a difference among all the metals. And the Friedman test successfully rejected the null hypothesis. And then, as a second step, we apply this pairwise test, which is an invention test in this case. So we test all the different methods in a pairwise way. So here are the results of the dimension test in the big table. So actually, you will see that this is the rank for all the methods for each different metric. As you can see here, even though we have 7 data sets, it's quite a lot for the label classification. But from a statistical point of view, it is still a very limited number. So in the test, we have some problem to find statistic significance. But nevertheless, the big picture is very clear, right? I mean, we almost always, actually we always is the first one, and consistently outperform the American and other baseline. So this is the big message, all right? Yeah, I'm pretty much done here. I want to wrap up with some conclusions. We have proposed a new approach to instance learning. Even though we have applied it in the multi-label setting, but actually this approach can be applied for classification in general. And the key idea is rather simple. We consider the label information in the neighborhood as an extra feature. And by using logistic regression, we balance between the global and the local inference. Basically, the two parts is one is a bias term, another part is evidence from the neighborhood. We balance it with logistic regression with the parameter alpha. And one way to say this, when you're using this approach, you can take the correlation between labels into consideration. I think that is the major reason why we can outperform the American on a large scale. And of course, in the paper, we have some other extensions. Like, for example, we also combine these normal features, insta features together. But I won't go to details here, so if you're interested, you can check the paper. And one last thing I want to say is, this approach is now publicly available in this Mulan Java library. Mulan is a multi-label classification Java library, open source, and which is maintained by the machine learning and knowledge discovery group in the University of Thessaloniki. And if you want to know more information, you can just check my website, and you are welcome to try our approach in this Mulan package. So this is all from my side, and I would like to answer your question, and if you have any comments.
So, are there any questions?
So you say the good performance is due to the fact that you consider label correlation.
I believe this is one very important reason.
Yeah, you believe it, but did you check it? And there are different ways I think you could find out. One is to actually look at the coefficients that have been learned in some of these programs.
Yeah.
Whether they actually make sense that the basketball is high for football or something like that. I mean, this was not one of the problems, but I'm sure that.
Yeah, actually, I think.
And the other thing I think is, I mean, I would say that some of the good performance is due to the fact that you simply consider the neighborhood, and maybe not the correlation in the neighborhood. It's the correlation to the same label in the neighborhood, so that could be checked in classification problems. Did you do that?
Actually, we did that. I didn't show it here, but we did that. If you remember that in the content section of the multi-label workshop, actually, Greg showed a picture which showed this big circle to show the correlation of this And actually, if you do the same thing, you actually end up with almost similar figures. And another thing to talk about is the good performance maybe is due to the growing constant local region. And that is actually one major reason why MLKNN is so good. The insight-based is so good. Actually, we do the same thing as MLKNN, but actually the essential difference only in the local correlation. The MLKNN also consider local region. So we believe this is the and actually, we also plan to somehow join this alpha coefficient, like correlation to show a picture. But so far we didn't do it yet. But
can you use something else than KNN to generate the extra features? Like as we have more random forests over here.
I'm sorry, the first sentence.
Can you use something else than KNN to generate the extra features? Why KNN? KNN has many deficiencies, right? It couldn't work within multidimensional domains. This in domains with noise and
The major reason we using MLKNN and using the neighborhood information to generate the feature is actually the two things. First of all, this was somehow is motivated by the MLKNN approach. So the starting point is some based approach. And if the idea is to combine the global information and local information, and of course, if you think about how to make use of local information, the first thing you think about is KNN approach. And the SLN approach is more global. We call it a model-based approach. Yeah, it's sort of like this. This is how we start to think about this problem.
But did you try to generate these features with something else than KNN or not?
So far, we didn't try that.
I think it would be great.
That is a good point, and we could also think about how to use another methods to feature selecting or feature generation. Thanks for that. Okay, maybe.
Okay, if you evaluate your method on the test set, you use the neighborhood of the training set. Or also do you use the instances you classified in the test set?
Okay. Of course, whenever I talk about labels, I take it from the training data. Because you can only take it from the training data. Because only the training data you know the label information, right? The test data you don't know the labels.
Yeah, but if you classify some labels and you know the confidence value of the label, you can use this information to enrich your neighborhood.
That's true. I mean, I think what you said is if I know when I finish testing an instance, then you could use this information, right? Is that the point? Yeah, of course. And if you finish testing that, and in practice, you should definitely, if you got good feedback, you should definitely put this also into your training data. Right? So yeah, in a sense, it's right. Okay. Okay.
So the MLKNN classifier, does it consider some sort of weights, or is it more than rather voting? Because I mean, this is about Yuki's questions, because you said that. I mean, the difference between MLKNN and your approach is basically that your approach does consider the correlation between the outputs.
Yeah.
But well, as far as I remember, KNN from the KNN classifier doesn't consider any sort of weights.
You mean MLKNN?
Yes.
Actually, that depends on how do you think about it. Because MLKNN is actually also starting from base inference. So basically, the information is weighted by the product. And actually, the product is actually getting from the training data.
Okay, but I mean, there are no weights in use such as in your classifier. I mean, you could also use the weights from, I don't know, from the distance or from some kernel or something.
You mean for MLKNN or?
For MLKNN.
Yeah, I think they could.
Okay, but you didn't do this, yes? Okay.
Yeah, but
okay.
yeah, this is.
So this is another difference between your approach and MLKNN. that could be
let's say about it.
relevant to performance.
Actually, ML can then also weighted on the label information for another label information. And I think you could also say improve the ML can in that sense, also consider the label correlation. And actually, I never say that consider the correlation between labels. You can only do it this way. Of course, you can do it another way or other ways. But the most important thing I want to point out is whenever it's possible, you should consider correlation. But of course, there are more ways to do that.
I just wanted to say, if you want to underline the importance of correlation, you should compare it to a KMN approach, but also you use weights.
Ah, okay, yeah. For the sake of fairness, that's exactly true.
Any more questions? Let's thank the speaker again.